We're good. We're good.
Now I gotta get out of here without, oh, knocking it. All right, so you're being recorded then.
That's kind of scary.
Okay. How does the power company get the power from the generator to your house? You know that? Sit, James. Thank you. Sit.
Wires.
Here we have a circuit. It includes, what do you suppose that stands for?
Battery. Generator.
That's the generator. The difference between that and a battery, okay, now we're gonna minimize the amount of walking around the room you do while the camera's recording the clip.
About that.
Either way, you're crossing the
I've got living proof that you did it. Okay, we have the generator, and we use that little sine wave type thing because that's the kind of current that's generated by a coil of wire that's spinning in a magnetic field. Did we talk about why that was?
What's the type of current?
If this is a coil of wire, that's the south pole, that's the north pole of the magnet. And I turn the coil like this, what happens?
The current starts going through.
There's
What's the
force
current
against
when it's
it.
turning right here?
No.
None, because the velocity of the particle is parallel, or the protons are parallel to the field. As it turns like this, more and more of the field, or more and more of the velocity is perpendicular to the field's that way, so there's gonna be a force on the particles driving them this way. It's gonna be maximum right there because all of the velocity is perpendicular to the field. And then what happens?
It goes back to being,
It's,
Or
here's
it's
less and less and less of the velocity is perpendicular to the field, so less current until we get to here where there's no current at all. And then what happens in this piece?
it like,
Oh,
the
it goes to
switches
the
the opposite
switches
way.
current.
The current switches direction, right? It was toward me, now it's gonna be out toward you. So if we made a graph of that current versus time, it would start at 0, go to some maximum, decrease back to 0, and then go the other direction for a while, and then go to 0. What does that look like? It looks like a sine wave, right? And this is what's called an alternating current. Otherwise known as AC. What is DC?
Direct.
Direct current. That's the kind of current that's put out by a battery or something like that, by a chemical reaction. Okay, so we have an alternating current generator. And we have to get the power, the current that it generates to your house. How do they do that?
Through wires.
They string wires, don't they? So when they take the wires and they string them to your house, all the way to your house, that's miles and miles, isn't it? Okay,
Is it like the telephone poles?
yeah, it's the high wires. Usually the phone wires and the cable wires are the ones that are down low.
Okay.
And the big, tall, high ones are up there because they're the ones that are really dangerous.
Don't some have them underground?
It's much better in Houston to have them underground, to have them buried. But they only started doing that in new subdivisions and stuff. Why do you think buried is better?
For storms.
What happens out here all the time?
Power goes out.
We have power failures, right? Because tree limbs fall on the wires and stuff like that. So yeah, in Houston with hurricanes and the storms we have, it's much better to have them buried. Costs a lot. Okay, so as they go through, but in either case, there's a certain amount of resistance, and the farther it is from the power company to your house, the more resistance those wires have, right? So how can we deal with the fact that we have current going through wires? What gets lost?
Electricity. Power.
Right? Power is I squared times R, so whatever the current is that you send through the wires, times the squared times the resistance you have, that'll get lost on the way to your house. So,
We need to keep the resistance out there.
well, how would you minimize that? You could decrease the resistance, right? increase the resistance, you lose less. But there's only so much you can decrease it. You know, you still have to get it from the power company to your house. So we need to do something else. And so instead of having a direct connection here, here's what they do. They have like a coil of wire. And when the current alternates, it goes back and forth, it goes from 0 to big, to small, to negative, to small, to big, you know, like that. What is there in the space around a wire if there's a current in the wire?
Electric field.
Not an electric field.
Static electricity.
Magnetic field.
Maybe. Let's take a look at this.
You should. You should.
It's not static electricity.
It must be so good though.
Yeah, I'm not gonna see it, I don't.
Is that going on?
Let's do the first one.
Okay, now this is a video that was actually taken by a student last year of a demonstration that I usually do, but it shows it so much better on the film than it does if you all had to stand around and watch, that I thought I'd show that instead. Here.
This is getting.
Okay, now, what you notice right now is that the compasses are all kind of pointing. See the compasses around the wire?
When I turn the current on, I want you to watch the compass needles and see what they do.
What do they do?
They turn. They go back and forth.
They
Well,
magnetize.
they're kind of pointing like
In a
this.
circle.
Now, they're kind of, and if we had enough of them, you'd see it's not really a square, it's a circle, yeah. And,
So what is there that makes the compass needles point that way?
okay, now,
Magnetic
this gives us,
magnetic field.
first of all,
Magnetic
it shows
field,
us that this
right?
wire has a magnetic field.
I thought you said no.
There's a way we can predict what the direction of the magnetic field is by using a hand rule, your hand curled up like this, right hand still.
Right hand.
Okay, and get the direction of current. The current is going up here, right? Put your thumb in the direction of current, your fingers curl around the wire in the direction of the magnetic field. So this magnetic field, as we're looking at it right now, is clockwise, or counterclockwise, sorry, around the wire, right? So if we turn the current on, you can see them appear, see they get point roughly counterclockwise around the wire.
The same thing for this one,
The
but
direction
now
is
the current is down, right?
Anyway, explain the current going? The current's going up, and so, no, in this side only. The other side, notice it's the other direction, so counterclockwise here and clockwise here. Yeah, and that's this way. If we put a magnet up at the top, think about it, the current is going across the top, right? So if we're on top of the wire, the magnetic field should be toward me, and if we're underneath the wire, the magnetic field should be toward Inez. Look at, see now the needle's pointing at me, if I hold it above, and if I hold it below, it's pointing at Inez.
So what would be like this? Let the wire be here.
Below, what you do is you make your fingers go below the wire.
Oh, like this, okay.
Right, yeah, so your fingers have to be wherever you're trying to get the direction of the field.
Okay, I'm gonna
Yeah.
stop it there.
Yes, exactly, it's circling toward me here and toward you.
That's it on top, each of the on top one.
Yeah.
Okay, we'll come back to this.
Around the wire, there's a magnetic field or the coil?
Around the wire, it's And so if you wind the wire into a coil, there's still a magnetic field in the space around the coil, right? That make sense? Okay, and if the current changes, what do you think happens to the magnetic field?
Changes.
It also changes, right? Okay, so we have a magnetic field in the space around this wire, and that magnetic field is growing and shrinking like that. Gotta get a mental picture of this, which is not too easy. And here, totally not connected to the first coil, just next to it is another coil with a whole lot more wire in it. Sorry. Okay, if it's a lot more wire, what has to be true about the resistance of it? It's a lot bigger, right? But as this magnetic field pushes across this coil, what's gonna happen in this coil?
Wait, if
All
the
the-
right magnetic field pushes across through the
You
left.
have a magnetic field from this coil that grows, so it cuts across the other coil and shrinks and grows and shrinks. So we have coil wire, we have a magnetic field,
The current like
and
transfer.
we have relative motion between the two, right? What do we get? What do we get? I showed you this. If we take
A
this
current.
coil
A current.
and we put a magnet through it, right?
Movement and pull.
You get current, right? Didn't I?
Yeah.
Yes,
I know I
you-
showed you this. Okay, so if you have a magnetic field, you have a complete circuit, and you have relative motion between the two, you get a current induced. So because the current is changing in this one, there's gonna be a current induced in this one. And it turns out the power in this coil and the power in this coil will be the same,
Even though that.
right? But because, and that means, well, power is I times V or I squared R, but I times V. Because the resistance is much higher here, what's gonna be true about the current?
Much bigger.
It's gotta be a lot lower, right? So here we have a big current, here we have a small current, here we have kind of a normal voltage, I times V. If IV is equal to IV, if I is real small, what does V have to be? Real big. Okay, so we get the same amount of power in these, we haven't lost any energy. But here, it's low current, high voltage. Now, we cut the current, the value of the current. What does that do to the amount of power that's gonna be lost in these wires?
More
How that's going to be
powerful.
lost?
I mean, think about it. If we divide I by 10,
There's
do we,
less P
do
to
we lose
begin
less
with.
power or more?
Well, there's less power to begin with, so.
No, we start out with the same amount of energy, right here. But because it's very low current, when we send it through the wires, we lose less of it on the way. And we have more left when we get to your house. Does that make sense?
More than we started with?
No, not more than we started with, but this is a losing proposition. We're sending this power out to your house, and every second that the current is traveling through wires, power is just kind of, or energy is just kind of radiating out into the environment. And that's not so good, because what if you lose all the energy before it gets to your house and you can use it?
It's not good.
Not so good, right? But what if the power lost in the wires is I squared times R? If we divide I by 10, what happens to the amount of power lost?